All right, chapter 16, number 28. We have something called trimethylamine, the solution of it. And I just want to draw that up for you. So when you hear that amine root in the word, you've got a nitrogen, and this is trimethyl. So I know it has a lone pair because it has only 3 bonding pairs of electrons. Here are my trimethyl, 3 methyl groups. So that's trimethylamine. And I'm going to abbreviate it as R3 just because these are the same 3 R groups. And then really pronounce that it's not protonated, make it very, very clear, very obvious that there's a lone pair, and write it like that. So in water, and we've done this for weak acids, we write them as HA. And so these weak bases, we write them as some form of N lone pair. So in water, in equilibrium with its products, and because this is a base, it'll be governed by Kb, and they give us the Kb for trimethylamine. It's weak, it's a weak base. It's 6.3 times 10 to the minus 5. So because that's a base, it'll pick off a proton from the water and become a protonated molecule. So will now look like this. See the difference between this and this is an H+. So I don't have to write N lone pair H+. I'll just write NH+. Very similar to ammonia, NH3, and its conjugate acid, NH4+. Okay. And yeah, it's a base. So when it takes the proton off of water, it's leaving behind OH- in solution. So there I've got aqueous, and that's aqueous too, although it's getting a little crowded in here. That's a liquid, and that's also in solution. What must be the molarity? So of this solution, if the pH, it says at equilibrium, is 11.12. So my unknown is the initial concentration of the solution. We don't care what happens with water, and initially these are both 0. Some of it will dissociate, okay? So remember, all of this is dissolved, but because Kb is small, only some of it dissociates. So I can put all of Y in the beaker with water and it'll disappear, it's dissolved, but most of it is going to stay as R3N, and only a small amount, this many molar, will actually convert to the ionized form. Plus X plus X. So that at equilibrium, I have Y minus X molar, and X molar. Now I know what Kb is, but I still have 2 unknowns here, so let's solve for X. We are told that the pH at equilibrium is 11.12, therefore the pOH is equal to 14 minus 11.12, so that's 2.88, and therefore the concentration of hydroxide ion at equilibrium is equal to 10 to the minus 2.88, and that comes out to be 0.0013 molar. So let's slide this up. Now we're ready to feed it into the equilibrium formula. Kb is equal to 6.3 times 10 to the minus 5, and that will be equal to concentration of hydroxide times the concentration of the R3NH+ divided by R3N. And so basically that is equal to 8x squared over y minus x. We found out what x is, and we divide it by y minus x. And probably because this 10 to the minus 5 is small, and we have enough experience now to make the safe assumption that x will be small compared to y, and so I could probably take that out and just put 0.0013 squared over y and solve for y. However, it's not too complicated to keep going because this is not going to involve a quadratic formula. So 6.3 times 10 to the minus 5 is equal to 0.0013 squared over y minus 0.0013. Solving for y, so do your algebra, show your steps, and we will get an answer of 0.0281. And if we remember what we assigned y to, it was that initial concentration of R3N, trimethylamine, and that's what they are asking us for. And so the molarity of trimethylamine, this solution that has a pH of 11.2, quite basic at equilibrium, that is 0.028, 2 sig figs given the data that we were given, molar. And so that's your final answer. Another great question for the exam.